All right. Hey, everyone. I am Rohan. I'm going to be talking about the Linux graphics stack. I'm a consultant software engineer at Collabora, and let's get started. So before we get into this presentation, I am not yet an experienced graphics developer, and I would recommend that you take my words with a grain of salt and let me know if I'm wrong. So since we're at Linux App Summit, the core takeaway from this talk for you as application developers should be an understanding of how the Linux graphics stack works and the various components involved in the graphics stack. And as an application developer, how can you help debug issues while developing your applications on this stack? This presentation is not going to be about how to use graphics APIs or explaining what GPUs are or how to develop a GPU driver. That's kind of the big agenda that I'd like to kind of talk about here. All right, so the Linux graphics stack has essentially three major components to it. As application developers, you will be interacting with the graphics APIs, which are the first component. Underneath the graphics APIs are the GPU drivers, which are split into user space and kernel space. Within the Linux ecosystem, the graphics API implementations, as well as the user space drivers, live in the Mesa 3D software project, whereas the kernel space drivers live in the Linux kernel. As application developers, you will most often be interacting with either, in the Linux ecosystem, you will be either interacting with OpenGL or the Vulkan ecosystem. On the Windows system, for example, you would be interacting with Direct3D. I'm not going to be talking about that. So the graphics API. So what exactly does the graphics API give you? A graphics API is an entry point for graphics applications and libraries. It allows for abstraction of the GPU pipeline configuration and manipulation. Part of this pipeline is programmable, and part of this pipeline is configurable. And you have the choice of either OpenGL or Vulkan on Linux ecosystem, in the Linux ecosystem. As I mentioned before, part of the pipeline is programmable, and the way you program this pipeline is through either GLSL or HLSL. And these programs are passed as part of the pipeline configuration and are compiled by the drivers to generate hardware-specific bytecode. These are the use-based drivers I talked about just a couple of slides ago. So there are two philosophies when it comes to the graphics APIs. One of them is OpenGL, and the other one is Vulkan. OpenGL is the more traditional way of doing things, where it tries to hide as much as possible about the GPU internals, whereas Vulkan provides much finer grained control. Essentially, what this leads to is that Vulkan applications are much more verbose and more work for the developer, but less work for the CPU. This leads to better performances on CPU-bound workloads. This also means that Vulkan drivers are a lot more simpler. So since GPU is a fairly complex piece, we have the drivers for them are fairly complex as well. And not all of the code that you need to run on a GPU needs to be run in a privileged context. For this reason, we split the code between user space and kernel space. This also leads to easier debugging, since debugging in the user space is a lot more easier. So first, I'm going to be talking about the kernel drivers. There are a couple of responsibilities that the kernel driver deals with, such as memory, command stream submission and scheduling, interrupts, and signaling. These kernel drivers with open source user space drivers live in the Linus tree, and they are in drivers GPU DRM, whereas kernels with closed source user space drivers are out of tree. So the first thing that kernel drivers, that the kernel GPU drivers need to deal with is memory management. In order to perform memory management in the kernel, in order to perform any sort of graphics related tasks in the kernel, we have something called the DRM framework. Within the DRM framework, there is a memory management framework called, there are a couple of memory management frameworks called GEM and TTM. Before we get into GEM and TTM, there are a couple of terminologies that I'd like you to be comfortable with. A buffer object, for example, is a region of memory to upload GPU data, such as textures, vertexes. Just treat it as a region of memory, essentially, for now. An ioctl is the most common way for applications to interfere with device drivers. And a command stream is a set of commands compromising a full job on the GPU. Everything good with that? Everyone good with that so far? All right. So TTM is the older well, TTM is only used by one GPU driver that I'm aware of, which is VM graphicsware. Most other kernel GPU drivers will be using GEM. So that's the only one I'm going to be talking about. So GPU drivers using GEM expose ioctls to do memory management tasks such as allocating buffer objects, releasing buffer objects, mapping buffer objects into GPU memory, and so on and so forth. They also provide a way to do cache maintenance, and they also guarantee that buffer objects referenced by a GPU job are properly mapped on the GPU side of things. On the right, you'll see a couple of examples of these ioctls. So you can see there's one which creates buffer objects, maps buffer objects, and gets the buffer object offset, or the offset in memory, essentially. The next part of a GPU, the next responsibility of a GPU driver is scheduling. Typically, when you submit a GPU job, it does not mean it will be executed immediately. There might be several processes using the GPU in parallel, and the GPU might just be busy when the request comes in. So essentially, submission means that you queue the command stream, and each driver has an ioctl for that. Since these jobs can have inter-command stream dependencies, and the user space driver knows those, the kernel space scheduler needs to know that as well. And DRM provides a generic scheduling framework called DRM Shed, which allows you to pass that information from user space to kernel space. So now that you have your memory, now that you have your job submitted to the GPU, how do you synchronize between the kernel space and the user space? What happens essentially is on the GPU side of things, an interrupt is fired, and this interrupt gets reported from the kernel space into user space. In order to propagate this information from kernel space to user space, we use sync objects and fences. Fences allow for one job to wait on another, and sync objects allow for user space to be notified when a job has been completed. All right, everyone get so far with the kernel space side of things? If you have any questions, let me know in the chat. All right. A couple of questions coming in on the shared notes. I'll just wait for them. Right, so command streams are submitted. So the question is, how is the command stream submitted? Does it also live in a buffer, or is it sent via ioctls? So the command stream is submitted via ioctls. Essentially, there is a structure that you fill out with a list of commands and submitted via the ioctl to the GPU, to the kernel, which schedules it on the GPU. All right. So moving on to the user space driver, a couple of roles of the user space driver are exposing one or several of graphics APIs, such as OpenGL or Vulkan. It also maintains, which involves maintaining the API-specific state machine, managing any kind of rendering context, compiling shaders, the ones that we just talked about earlier, which are written in HLSL or GLSL into hardware-specific bytecode, creating and populating and submitting command streams, interacting with the Windows system, and synchronizing on render operations, and essentially most of the functionality that you will end up using in user space. So there are a couple of graphics APIs that are provided by Mesa. So the first one is OpenGL, and it provides a front end for OpenGL and GLES. The modern day drivers make use of something called Gallium, which is a state tracker within Mesa, and the drivers are shared libraries that are loaded on demand. Whereas when it comes to Vulkan, Kronos has its own driver loader that is open source. Mesa only provides the Vulkan drivers, and there are no abstractions for Vulkan drivers or state tracking, and code sharing is done through libraries. So let's get into Mesa state tracking. This is the pipeline configuration part of the GPU pipeline. I'm not going to be talking about pre-Gallium days. A bunch of drivers such as i965 and i915 use this, but they are more or less on their way out in favor of Gallium. So what exactly is Gallium? Gallium is a state tracker that allows for tracking OpenGL state and allows for easier driver development, essentially. What happens is that Mesa will implement the OpenGL on top of Gallium, and Gallium consumes functionality provided by device drivers, which further consume functionality provided by the kernel space device drivers. This allows for much more easier creation of command streams and jobs, as well as making sure any buffers that need to be synchronized get synchronized properly. And it takes off a lot of work out of developing a driver. When it comes to Vulkan, Vulkan doesn't have Gallium. It only simply interacts with the kernel space drivers directly. All of the state tracking, for example, will be left to an application developer. Right, the next part is the Mesa shader compilation part. This is the pipeline manipulation part, or the programmable part of the pipeline. So shader compilation usually follows a couple of steps. What it essentially means is that a language such as GLSL or HLSL gets converted into a generic IR. This IR gets optimized by Mesa over a couple of passes, and then this generic IR gets converted into GPU-specific IR, and then the GPU driver performs optimization in the GPU-specific IR space. And then we have the bytecode generation, which essentially compiles this GPU-specific IR into bytecode. So what does this actually look like? Kind of like this. So let's say you have a GLSL program, and the way it will work is that the GLSL will be converted into GLSL-IR or SPIRV, for example. This GLSL-IR will then be converted into TGSI or NIR. And between each of these passes, there's also an optimization pass going on. So once you convert GLSL into GLSL-IR, it'll have an optimization pass. And then if you convert it into NIR, it will also have an optimization path. This NIR then might be converted into Midgar IR, for example, by the device driver itself, which will then be further optimized and then finally converted into bytecode. This is one of the most tricky parts of writing a GPU driver from what I've seen, simply because on GPUs such as the Mali GPUs, there's practically no available documentation on how to convert this NIR or intermediate representation into GPU bytecode. This is where the bulk of your development efforts get spent on, essentially. It also has a big impact on driver performance. So we really want to make sure that the driver, like this bytecode compiler, is as optimized as it can be. So debugging tips. As application developers, this is probably one of the most useful parts of the presentation for you. So GDB is a friend. Get comfortable with it. Essentially, if you've done any sort of OpenGL programming in the past, you will recognize that there's something called GL get error, which allows you to get errors from the OpenGL implementation. Within Mesa, this is implemented with the _Mesa_error function. And if you essentially break on this function, you will have a backtrace of exactly where Mesa stopped executing or where exactly Mesa threw an error. If you use a particular GL function, such as GLGen textures, the equivalent Mesa function for that entry point is _Mesa_foo. You can break on any of these functions to start stepping into the Mesa implementation of a GL call. While you're debugging, enabling your sorts is also a great way to ensure that all the conditions are being met and satisfied in the code. You can also set the Mesa debug environment variable, and you can check out every single driver has its own environment variable for debugging as well. And I would recommend that you go to the link that's mentioned in the slides for a complete list. Piglets. The piglet tests are one of the best ways for you to, as an application developer, to either understand a particular feature or a GL call. Piglet tests. Mesa has a comprehensive piglet test coverage, and simply using GDB on one of the tests and breaking on any of the functions that you need to debug or understand is a great way to have a minimal test case or a minimal entry point, essentially. All right. So the GPU topic is quite big, and it can be intimidating. I have been working on this for the last year and a half, and I still definitely have a lot to learn. So I would recommend that you start small and choose a driver and stick with it till you understand large parts of it or the larger theme of the driver. Maybe find a feature that's missing or buggy, and just don't give up. Just keep at it and come hang out with us on IRC, ask questions. There's a whole bunch of nice people who will help you and try to kind of get things working. Things take a while, but if you just keep at it, you'll do great. These are a couple of good resources that I would recommend that you read to just get a general overview of how OpenGL works or how GPU works, or to get a better understanding of the DRM framework in the Linux kernel. And also go check out my colleague's talk at ELCE. There's a whole bunch of talks that come out at ELCE that are great resources to learn specific things about the GPU driver community, I would say. So go check those out on YouTube. And that's it from my side. Does anyone have any other questions? All right, so one of the questions is, which bit of the framework is responsible for shaders and where do they get injected? So shaders essentially are programs that application developers will write. Let me see if I can go back a couple of slides. All right, so shaders are written at the application layer over here, and they get passed to Gallium, and then they get passed to the use-based drivers. And these are essentially programs like C or C, they're C-like programs, and they get compiled just like you would compile, for example, a C program. They have a compiler, and except in this case, every single driver has a compiler. There isn't a standard GCC compiler. And in order to compile these programs, you first have to convert them from this C-like format to a IR format, such as NIR or TGSI. Does that answer your question? Awesome. One of the other questions was, I think someone asked, why are NVIDIA drivers so buggy? Jonathan, I have no clue. I think writing GPU drivers is pretty difficult, especially when as a company you have to support a wide range of products across a wide range of platforms. We as Mesa developers have a slightly easier job that we only have to kind of support Linux at the moment. And the fact that we have such a large and active community also definitely helps. I think if NVIDIA kind of wants to come join us in the Mesa world, they should definitely come do that. Maybe we can learn from each other. So the next question is, what is the status of Vulkan integration in Mesa? Let's see. So that's a tricky question to answer, essentially because of the fact that there are new standards coming out. Every single time you have a new OpenGL standard coming out, there is new functionality that needs to be implemented. So the answer would be, it's never going to be complete. And so at the moment, I don't really know what percentage of the tests are passing, what percentage of the Piglet tests for Vulkan are passing. That is something that I would need to go and look up. But from my understanding, it is in a pretty good shape. I've definitely seen games running on Vulkan on Linux. So decently complete, enough to run a game complete.
Thank you so much, Rohan.
All right. You're most welcome.
We still have a couple more minutes in case anyone wants to add another question. Otherwise, thank you so very much, and I hope you enjoy the rest of the conference and you're able to stay and watch with us.
Absolutely. And if you have any more questions, I am Shade Slayer on IRC. You can throw those questions over there. We have a bunch of IRC channels. Come hang out with us.